So we are going to almost finish up our review. We got just Unit 12 tomorrow, but let's start by talking about our grades. And a lot of you in this class are probably sitting fine with your grades and you don't need to worry about this, but some of you are and needing to kind of think about how to bring your grade up. All work for credit must be turned in by Wednesday evening. I didn't put a time there, so let's just say by midnight on Wednesday. Okay, and that means here's the list of all the stuff, and you can come back to the presentation to make sure you got all this. Any old missing homework assignments you can turn in for half credit. You can you can do those review FRQs that I've been assigning every night. You will have to do the work, turn it in. You don't have to get it right, but I just need to see that you're doing some work. And the basic idea is when I assign these, and this is how you're gonna get the most benefit from it. You're gonna get the most benefit from doing the FRQ, coming to class, and we'll talk a little bit about it, and you can get further explanation on it if you need it, but you're better off having some kind of a foundation that you've done with the problem and then finding out what you did wrong rather than finding out what the answer is without thinking on your own. Okay, but anyways, do those review FRQs. Any progress checks you haven't done, the practice tests, make sure you're doing all of those. And of course, the project, I'm going to go through and grade those pretty soon, but if you have not finished part of that, get it turned in. And don't forget about test retakes. So you might want to make a note right now. You can stick around after class if you wanted to let me know what retake you plan on doing. And that is pretty much it for grades, but this is crunch time now. It's the last week. Make sure you're getting it done. FRQs. You were assigned an FRQ for Unit 8. It was a pretty simple FRQ, I think, as far as FRQs go. So there's not a whole lot to it. It's a pretty straightforward problem. So what I want you to do is just talk about the entire thing. Go ahead and mention what you got for your answer for part A. And the second part was a conceptual question, and you can answer that one really quickly. It shouldn't take you more than a minute to do that. Unit 9, I want you to talk about parts A and B. And again, if you looked over that one and answered it, you already know that A and B, you didn't have to do calculations for it, but it did require understanding and interpreting some things and coming up with an answer, obviously. That didn't need to be said, but thinking through things conceptually. So go ahead and talk about what you thought for parts A and B on that. I will give you about 4 minutes in breakout rooms. And let me real quick create the breakout rooms for you. Okay, so the breakout rooms are created and I will go ahead and let you spend about 4 minutes in there. Okay, so this is the only little bit of it that I wanted to talk about. So first of all, let's just answer this. This is from Unit 8, Part B. From the analysis that you guys looked at, can the estimate of the mean swimming speed be generalized to all types of penguins? Anyone can answer this.
I don't think so.
And why can't it?
Because, wait, I'm sorry. Oh yeah, I think it generalizes to like the emperor penguin population, not all penguins.
There you go. That's it. So they only looked at emperor penguins. That's all we can generalize it to. Pretty straightforward. Trying to think if there's anything else I need to say about that. It's pretty simple question when it comes down to it, but you will have to investigate if you have a question like that to see where maybe the problem is. But keep in mind that this was a confidence interval for means. And so just in general for means, I'm going to go ahead. I'm not going to put the general statement, but the specific statement here is going to be your X bar. Oops, I should write. So it's going to be X bar plus or minus your critical value. Oh, sorry. For critical value here, it's going to be a T star. And it's going to be your sample standard deviation divided by the square root of n. Okay, so you needed to use that formula to come up with your confidence interval. And the T star would have used degree of freedom. Well, it was a sample size of 31. So your degrees of freedom would be 30. And notice how they set that up. so that it was 31 is a weird sample size, but it happens to be so that we get 30 for our degrees of freedom, which is what we need. So for AP problems, they want to make it so you can find your t-values on the chart. You don't need to use technology for anything like that. All right. We can move forward with that. I'm not going to do the calculation. Clark, well, I'm not going to read this, but basically for part A of the Unit 9 FRQ, we had a confidence interval already created. And does this confidence interval provide convincing statistical evidence that the number 6 will land face up more often on the baked die? You can just say yes or no, and if you have a reasoning for it, what do you think?
No.
Okay, it does not, and I agree. And why does this not provide convincing evidence?
Because the confidence interval includes the 16.7% probability that a 6 lands face up.
Perfect answer. There you go. So I just quickly calculated our confidence interval goes from 0.158 to 0.272. And if you did the FRQ, you already have that probably. But just like Zach said, 0.167, that's 1/6. So 0.167 is the expected number, proportion of rolls that are going to land on 6. That is included, just like you said, in this interval right here. So we can't conclusively say that 6 will roll face up more often. All right, but when we get to the next problem, they did a significance test, significance level of 0.05, obtained a test statistic of this, most importantly, a p-value of 0.033. Does this agree with the confidence interval conclusion?
No.
No, it does not. So essentially, what is our outcome from our significance test?
She rejects the null hypothesis of a 1/6 probability, whereas the confidence interval includes it.
Okay, so there we go. We can see that we get kind of conflicting ideas going on. So just, yeah, perfectly said. So our p-value is less than our significance level, so we reject the null hypothesis. And we don't say it this way, but essentially we're rejecting it in favor of the alternative hypothesis that it was higher than 1/6. Now we can probably see why this is the case because, and I'm just going to talk through this part. If you create your entire confidence interval, so here's the point estimate, here's the confidence interval, it goes from 0.272 down to 0.158. Well, 0.167 is going to live somewhere around here. All right, so only this part of the confidence interval would contradict our significance test. But the rest of it, the vast majority of this confidence interval agrees with our significance test. And so we can just get this little bit of gray area where one of the tests doesn't quite give us the convincing evidence and one test does. So those situations can happen as long as you're aware of it, you're cognizant of how all these tests play with each other and stuff like that. Hope you know what I'm trying to say. All right, let's look at Unit 10. Inference tests for 2 samples. Okay, that was Unit 10. This was, according to test scores, this was definitely the most difficult test that we had all year. So your test statistic here is going to be the stat minus a parameter divided by the standard error. You can substitute in, and of course, here's a confidence interval general formula. But of course, the reason I showed that is because when we're dealing with 2 populations, we could have 2 sample proportions that we're getting a difference of, or we could have 2 sample means that we're getting a difference of down here. And the parameter is given right here. Here's our parameter. In fact, let me just write it this way. This is, you are hopefully aware, this is coming straight from the AP formula sheet. There's our parameters. Here's our standard error given in this column, and the statistic is given right here. So if I know where to find those things, I can just plug them in. And I have to know what they mean in context, but we're good to go with that. The critical value comes from the AP formula sheet as well, which we're not going to look at that right now, but I'll pull that up a little bit later for one of our problems. So as complicated as it is, the calculations, we can find the formulas to plug in. There's a lot of conceptual things going on. One thing to remember for our standard error, especially, well, only with proportions, is that when we're dealing with this, we're always assuming that our two population proportions are equal. So we want to do a pooled proportion. And that's where you take your combined counts divided by your combined sample sizes. And that might have been something that you've forgotten, kind of got lost in all the other concepts that we've talked about, but your pooled sample proportion is going to be what you use here. And you can see where they plug that in here. All right. So, and just to clarify, and this should be obvious to you guys, but this is the same as this formula right here. It looks a little different. This is the same formula. We just are using p hat sub c for everything up here. And they just decided to distribute that, use distributive property and pull that out. Okay, I think that's enough said about this. Let's go ahead and look at some practice problems, because a lot of these are conceptual problems. And that's where we'll dig into it a little bit more. All right, the general manager of a car dealership is curious if a flat discount will bring in more customers than a % discount. She sends out 500 coupons for $1,000 off the sticker price to a random selection of residents, and 400 coupons for 3% off the sticker price to a random selection of residents. The dealership then records how many come in with each type of coupon. Assuming the conditions for inference were met, what test procedure should be used to answer the general manager's question? So we can see that we're comparing two different samples, because we got a sample of 500 coupons. We got a sample of 300 coupons. So we do have two samples. And with a question like this, you might be looking at it for a few seconds or maybe more than a few seconds trying to figure out, well, is this proportions or means? It's kind of hard to figure that out. Now, just in general, I will say that if it doesn't mention anything about standard deviation or means anywhere in there, then your default is to come back to proportions, okay? Because proportions can be talked about in different ways. Means, they're going to need to give you the standard deviation somewhere in there if you're going to do anything. So without any of that information related to means, I'm going to say these are two. So it's two samples. And it's proportions. So that'd be a z-test. Well, and here's where we have to be careful. Is it a z-test or a z-interval? Well, they're trying to figure out if one brings in more customers than the other. And either one of them could technically do it, but I think a straightforward z-test is the most straightforward. And luckily, it doesn't even give me z-interval as an option. So anyways, it's going to be a two sample z-test, which I know means it has to be a difference between two proportions. So there it is. All right, next one. A biologist found sample proportions using two independent random samples, assuming all conditions for inference are met. Which of the following is the best method for the biologist to use to estimate the true difference between the population proportions? So luckily, I mean, it tells us a lot right off the bat. It's proportions and it's two samples. So two sample, and it's going to be a z something. So now I'm going to jump to the next question. It says, what's the best method for estimating the true difference? A significance test doesn't tell me anything about what the true value is going to be. It just says whether this difference is statistically significant. So a z-interval is what we want to use here. So I will construct a two sample z-interval for the difference between the two sample proportions. Oops. not that. I screwed up. It's not a sample proportion, it's population proportions. Okay, so that's what we want to be doing here. Good thing to read through all your options. And I just showed you case in point. Okay, a large number of randomized experiments were conducted to determine whether sleeping for 8 hours would improve performance on memory tests. Each of the experiments, the treatment, for each of the experiments, the treatment effect is the difference between the proportion of people sleeping 8 hours who passed the memory test and the proportion of people sleeping 6 hours who passed the memory test. If the amount of sleep had no effect whatsoever, which of the following experimental results would be anticipated? So we are going to answer this question assuming that the null hypothesis is true and that the amount of sleep has no effect. If this is true, we're going to get a distribution that the difference between P sub 1 and P sub 2 is 0. And again, assuming that this is true, randomly, we could get results that happen anywhere in this sampling distribution. We could get a result that ends up here, or here, or here, and so on. So all these are possibilities. We're going to expect most of them to fall somewhere close to 0. But if we look at this, p-values will be greater than 0.05 about 95 for about 95% of the experiments. Well, that makes sense. That seems true because the 0.05 is the area under the curve. There's 5% of the area under the curve there. So we would say that 5% of the time, just by random chance, we're going to end up there, which means 95% of the time, we're going to be greater than 0.05. Okay. So hopefully that made sense. And there you go. That one is true. There will be about an equal number of experiments showing positive and negative values of drug effects. This is assuming we did this experiment many times. And we would expect to see about half the time the difference is negative and half the time the difference is positive. And that seems true because it really hovers around 0. So it's going to be on either side of that. When 95% confidence intervals for the population drug effect are constructed, these confidence intervals include 0 about 95% of the time. And this is kind of interpretation of confidence intervals. Remember that your confidence interval is going to be based on a sample proportion or difference of proportions. And if we had this kind of diagram that looked like this, and we could have a lot of different confidence intervals created, and 95% of them should capture this true mean right here. But every once in a while, you might end up, I'm going to draw one right here, where this one, because we're dealing with this sample mean right here, it doesn't, or that sample proportion, difference in proportions to clarify, it doesn't quite capture that 0, but that's only going to happen about 5% of the time. So 95% of our confidence intervals should capture 0. All three of these are true. And there we go. We can move forward. All right. Just going to check something real quick. Okay. Unit 10, in order to determine the durability of laptops, certain models are dropped from a height of 3 feet until they no longer function. A random sample of 30 laptops was selected from each of 2 manufacturers. They were dropped and tested until they no longer would operate normally. The difference in mean number of drops was recorded and used to construct the 90% confidence interval to estimate the population difference in means. Imagine that this procedure was repeated, and each time the results were collected, a new 90% confidence interval for the difference in means was constructed. Which of the following statements is a correct interpretation of the intervals? So we are just interpreting intervals at this point. All right. And we're going to construct a lot of them over and over again, just like we talked about. If there's the true mean, 90% of them are going to capture. Let's say that one just barely captures it. This one does. If I drew 10 more, so I'll just put ... Well, maybe one of these doesn't quite capture it. So 90% of them should. And so if I go through, we're looking at two means, so mu1 and mu2, but what we're doing is we're estimating the difference between those. So this is the parameter that we are estimating. Now, when we say we capture it, we're capturing the true difference. So it's important to point that out because this first one says approximately 90% of the intervals constructed will capture at least one of the population means. So saying we capture that one, but that's not what we're estimating. We're not estimating what one of those means is. We're estimating the difference. So it's not that. All these intervals will be a little different, and unlikely they're going to be exactly the same. Okay, approximately 90% of the intervals constructed will capture the difference in population means. That one looks promising. Approximately 90% of the intervals constructed will capture the difference in sample means. No. Every single interval will capture its own sample mean because it's going to be right in the middle. Approximately 90% of the intervals constructed will capture at least one of the sample means. And again, we're not talking about capturing one, we're not talking about sample means. And just to explain the idea that each interval is going to capture its own sample mean, that's the difference in sample means. That is, this point estimate is the difference in sample means for every one of them. So that's always going to be right in the middle. We don't care about that. We're using that to estimate this value right here, the difference in population. Okay, enough said about that, I think. Let's look at the next one. A naturalist examining whether the number of fish caught in a stream basin has changed since a fire burned in the watershed, or she is doing that. And data in the form of fishing reports was available for a 5-year period before the fire. From a random sample of 195 fishing reports before the fire, the mean catch was 6.3 fish with a standard deviation of 1.6. In a random sample of 143 reports 3 years after the fire, the mean catch was 7.1 fish with a standard deviation of 2.1. Which of the following represents the standard error of the difference in the mean number of fish caught before and after the fire? We're only asked about the standard error, and standard error for means is just, so let's put X bar right here, is going to be the square root of S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. And I'm not actually going to plug this in and calculate it, or I'm not going to calculate, but I will plug the numbers in. So if I call the first one right here, sample 1, and then the reports after the fire sample 2, it gives me the sample standard deviation of 1.6 over the sample size of 195. And then if I look at the next one, it's a standard deviation of 2.1 over 143. So that's what I need to calculate, and that's what will give me the standard error. Okay. And remember, standard error is just a standard deviation, but when we're dealing with samples rather than populations, we call it standard error. Okay. This one actually asks us to perform the entire t-test. So we're looking at a difference of means. I've got all of my data right here, and we're trying to figure out, does region 4 pay higher salaries than region 7? And just on this line alone, it seems like they do. But is this statistically significant as a difference? So when we're calculating a test statistic for means, we're looking at, and I'm not going to do the stat minus parameter, that's the general one. So it's going to be x bar sub 1 minus x bar sub 2 minus mu sub 1 minus mu sub 2 all over the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And now if I plug numbers in, x bar sub 1 is 51,472 minus x bar sub 2 is 49,002. My difference in means right here for population, the null hypothesis that there is no difference. So I can just put a 0 right there. Now the square root of, it's going to be 6,274 is the standard deviation for region 4 divided by, and that's squared, divided by 117 plus 9,319 squared all over 78. So that's what I can plug into the calculator to get my test statistic. And then I can do a TCDF. Now we're going to do it a little differently. Remember, your calculator can do this for you. I wanted to write this out because it's important to show your work, okay? And that shows that you know what is supposed to go where. And you could do this by hand. But you can also just use, if you go to Stat, Tests, and then Option 4, you can use this to do the work for you. So on the input, first option there, you pick Stats, and then you can just plug in your X bar sub 1, your standard deviation for 1, and your in sub 1. So I'll go ahead and do that. 51,472 for X bar sub 1, 6,274 for standard deviation of 1, and then 117 for the sample size of 1. And then we can do the same thing for the next. 49,006, 9,319 for the standard deviation, 78 for the sample size. And now we need to think which one of these is going to be bigger. The alternative hypothesis is that mu sub 1 minus mu sub 2, and this is going to be 1 and 2 right here, that region 4 pays more. So this is my alternative hypothesis, that this difference is not greater than 2, sorry, is greater than 0. So in that case, we're saying that mu sub 1 is greater than mu sub 2. So that's what I want to select for my hypothesis. And we can just calculate it at that point. And the p-value when I do that is 0.0213. So at this point, we can decide, is this statistically significant? Well, this is significant at the 0.05 level, but not at the 0.01 level. So there's our answer. And just on a different conceptual level, it's good to point out that you don't run your experiment and then decide on your significance level later. You need to decide on your significance level ahead of time in order for it to be good statistical practice. Okay, I think that's it for Unit 10. Right. If any of those you still needed some help on, just stick around and we can talk over those more. Unit 11 is dealing with chi-square tests, and we've got, of course, just in general, we're comparing distributions of counts. And we could have a chi-square goodness of fit test, a chi-square test of homogeneity or of independence. Expected counts. Now, with goodness of fit, we're actually going to have an a multiple choice question about this in a little bit, so we'll go over it. And we'll have one for these as well, but these are both where you take your column total times your row total, and you divide it by the table total. So remember that formula. It's not too bad, or you don't have to remember the formula, just remember the concept. And we'll have a little bit of that with our multiple choice questions. We don't calculate chi-square by hand. We could do that t-test that we just did. We could have done that by hand, and it wouldn't have been too bad. This one would not be fun. So if it's a goodness of fit test, we can just set up a couple of lists, one with observed, one with expected counts, and then run the goodness of fit test. If it's homogeneity or independence, we create two matrices and we let the calculator handle it from there. Remember, we have to go through, especially if it's a big table. So if it was a big table like this, we'd have to perform a calculation for this cell, for this one, 16 different calculations before we get to the last one where we add it all up, and then we're not even done yet. So that's very time consuming. That's why we let the calculator handle it. A simple random sample of 1,000 US adults was collected to investigate whether gender and watching live sports are independent. The results are summarized below. Which statement is true about whether the conditions for chi-square test for independence have been met? So with chi-square, we have three conditions like normal: random, 10%, and normal. It's an N at the beginning. Okay, so it does say it's a random sample. We're good to go. 10%, well, 1,000 is definitely less than 10% of the United States adults. And normal. The test for this is that your smallest expected count has to be greater than 5. And of course, we can see our smallest expected count is well over 5, so we're good to go. We have met all conditions. If this was an FRQ, we'd want to make a statement to this effect, But it's a multiple choice question. We just need to check it and move on. The State Highway Commission is considering removing the lane that allows people to pay cash for a toll on a toll road. All right, I'm not going to read the whole thing, but basically, are people in favor of it or not, based on whether they're in the northern part of the state or the southern part of the state? And we would need to actually calculate a p-value for this one. And I am not going to do that right now, except to show you that, remind you, I guess, that these cells right here represent your matrix A. And those are your observed counts. The expected, you need to create a different table for that and then plug it in for B. So I'll say this is matrix B right over here. And this is where you would actually do the calculation. You could do 200 times 201 divided by the table total. So 200 times 201 divided by 404 would give you 99.5. All right, and we can keep doing the same thing for all of these. And as we do that, we're going to get 100.5 right here. I can do the same thing right here, multiply by the row total. And then the column total, and then divide by the table total, which is going to be 101.5. And then I can do that same thing for this one right here. I'm making this kind of a mess on the left, but I'd get 102.5. And we can get, now the way that you can check this, just in general, is add across. So if I add these two together, I should get 200. And I do, so that tells me that I did that part right. And I can add across, and I'm gonna get 204 right here. Adding down, I'm gonna get 203. And then adding down, I'm gonna get 201. So that gets me the correct numbers for the marginal totals. All right, enough about that. Once you've got your matrices, you can plug it in, let the calculator do it. I am not going to worry about that part. You can do that in your own time. Okay, now this is how we come up with the distribution for goodness of fit. So it gives us a percent breakdown of, for this particular context, but in order to figure out the expected counts, we need to have a sample size. So we're talking about 230 animal clinics, and I can just, from here on, I can just multiply each one of these by 230. All right, and as I do that, I'm gonna get my expected counts, and we will get decimals. So just for the first one only, 230 times 0.61 gives me 140.3, which I see right here. If I keep going, this is the only one that gives me decimals. So almost without doing any work, I might guess it's that one, but of course you'd want to do the math to confirm it. And there you are. You can have decimals for expected counts. Or sorry, yeah, for expected counts. You cannot have decimals for observed counts. You'll get an error that way. Okay. Now we've got a new situation where we're talking about, of all cars with black seats, what's the percent breakdown of car color? So I'm only going to be talking about the car color. We know all of these are black seats. So it's going to be a white car is 0.43. And there's a reason I'm creating this. A blue car, so I'll put B-L-U, I'll just spell it out. I'll put blue, because we're going to have black in a second. And that's going to be 0.46. The next is red, which is 0.07. And the last is, does this even add up to 100%? This is black. It's 0.04. So here's a problem. It doesn't quite add up to 100%. So that's not a very good probability distribution. This is a flawed question. But That's okay. 87 plus 11. This is only 98.
Uh,
Oh, great.
It adds up. Yeah.
It does?
Yeah, because 0.46 plus 0.04 is 0.5, and then 0.43 plus 0.07 is 0.5, and then.
I don't do math well. That's my problem. Thanks for checking me on. Oh my gosh, I see what I was doing wrong. I was adding these two up wrong. It does add up. Yay. Thanks for double checking me.
For sure.
Okay. Now let's get back to the important part of this problem, not the part where I don't do math correctly. And anyways, we are going to check this chi-square statistic to figure out what the tail probability is, the p-value, in other words. And because it's 6.25, we don't know what that is until we know the degrees of freedom. I created this table because we've got 4 categories. And for goodness of fit test, we use number of categories minus 1. So I'll just, there it is. So we would have to go to the table. In fact, now I'm going to bring up the formula sheet. I don't need this writing anymore. And on the chi-square test, it was a 6.25 chi-square statistic. Degree of freedom is 3 right here. And I can see 6.25. This one was set up intentionally to show up on the chart. So that's going to be 0.10. So when I come back to this, I'll have to figure out how to do this. Okay, there it is. Now I can see that 0.10 is the answer. All right. Good times. And this is our last question to go through today. It's pretty straightforward. How many degrees of freedom should be used for this goodness of fit claim? Now, this is maybe a little bit tricky, hopefully not, because you could see Monday through Sunday, oh, that's 7. So therefore 6 is our degrees of freedom, which I guess is the intention behind maybe making this a trick question. But we can see that the categories are Monday through Thursday. I don't care about the numbers here. I'm just going to lay out the categories. And then we've got Friday, Saturday, and then Sunday. Those are the categories. So in that case, we only have 4 categories, and the correct answer is 3. Okay, so pretty straightforward on that. And that's it for unit 11, I think. Yes. So if there are other questions, I just have to add this caveat all the time. This is not a comprehensive review of all these units. It's just certain concepts that pop up that you were tested on. So anyways, now you've got 2 more FRQs for tonight. It shouldn't take you too long to do these. They're not so bad. For unit 10, only do A and B, though if you are planning on doing the AP test, I would highly encourage you to look at part C and D. We're just not going to go over that part at all in class. Though if you have questions on it, we can go through it after class. And you'll see part in number 2 for your unit 11. Just ignore it. You've probably gotten used to seeing parts of other problems. So that's it for today. If you have any questions, you can stick around. But besides that, you have a wonderful day, and I will see you tomorrow.